Hello, welcome back to Algebra 1 with Miss Betsy. We're continuing our discussion this week of how to solve systems of equations by using the addition method rather than using the method of graphing the lines on the same coordinate system rather than just using straight substitution. What we're going to be doing today is moving on to a little bit more difficult of a system to solve because you have to apply the multiplication property of equality to get the two equations in the form where you can add them together. But you're going to see that when I say it's a little more difficult, it really is just a tiny little bit more difficult. And I think that at the end of the lecture you'll see that there's really nothing to be afraid of at all with solving these systems of equations. This video is driven by the second edition of BJU Press's Algebra 1 edition. Doesn't track exactly with the third edition, but you can still use the same material to learn from, and you can learn about solving systems of equations regardless of what text you're using. So let's pray and go ahead and get started. God, I thank you for another day of life that you've given to us, and I thank you for the privilege of living here in America where we are free to educate our children, educate our young adults in so many different ways. Father, through this medium of internet teaching, Lord, I ask that you would help the kids and all of my students to be attentive, that I'd be able to communicate clearly to them. And we honor you in all that we do today. In Jesus' name, amen. All right, lame joke for today. Where do birds invest their money? Lame question for today. Where do birds invest their money? Well, they're just like people, except they invest their money in the stock market. And hopefully they get a little bit better return than you can sometimes in the stock market. So what we have been doing in the last couple of lessons is we've been finding solutions to systems of equations. And it sounds like a big bunch of words, but all you're doing is looking for the point where two lines intersect. And we saw that those lines could intersect, or two lines could relate to one another in three different ways. Either they could be parallel, as they are in my first drawing here, and if they are parallel to one another, there's never going to be any intersection, so there's no solution that works for both equations at the same time. The most common way that two lines relate to one another is they intersect at a single point in space. And we are able to come up with an ordered pair that describes and identifies and locates that point of intersection exactly. Then the third way we remember that two lines interact is they can be collinear. One line can be sitting right on top of another. So there are an infinite number of solutions to that system of equations because every place one line tracks, the other line sits right on top of it. And we've seen that it's really a straightforward method that we use to come up with the solution to these two equations simply by adding them together. We're going to put a little extra twist on this today. I'm on section 7.6, solving systems by the addition method, and we're on page 296. So let's see what our first pair of equations, what we have here. This is example 1, and it's on page 296. We have x plus y is equal to 8. We have 3x plus 2y is equal to 22. And what we've been doing so far is we learned that we could add two equations together because we would simply be combining like terms. X plus 3x, y plus 2y, 8 plus 22. And we found that when we added those equations together, with the problems that we've been working on so far, one of those variables here would cancel out because we would have like positive 2y and a negative 2y. You add those together and your y value disappears. And I apologize for the coughing. Still trying to get over whatever this junk is. And then we saw that sometimes if we subtracted, because subtraction is the same as adding the opposite, we saw that sometimes if we subtracted one equation from the other, that would also allow us to have one variable drop out. Now, however, we're coming to equations that look like this, a system of equations that looks like this. X plus y is 8, 3x plus 2y, 3x plus 2y is 22. If we add these equations together, we have 4x plus 3y is equal to 30. Well, that does us no good, does it? What if we subtract? X minus 3x, we have negative 2x, y minus 2y, minus y is equal to whatever this is. I think it's a minus 14. Is equal to a negative 14. Neither of these solutions here help us at all because we are trying to eliminate one of the variables. Now, what in the world are we going to do to be able to solve these equations? We have just one additional step that we need to add. Remember way back when we were talking about properties of equality, we said that it was true, that 3 is equal to 3. Or 3 was equal to 2 plus 1. And I'm sure that you thought, oh, well, it's really obvious that 3 is equal to 3, and I've known that 2 plus 1 is equal to 3 since I was 5. It's just that we were establishing the principle of equality, that different looking quantities can have the same value. And then we introduced what they called the multiplication principle of equality, and that told us that if we multiplied both sides of an equation by the same value, while the result looked different from the original equation that we had, it was still valid. 3 is equal to 3, 3 is equal to 2 plus 1, 6 is equal to 6. So we learned that as long as you multiplied, as long as you performed the same operation on both sides of the equation, everything was legit. Your seesaw was balanced. So it's the multiplication property of equality here that is going to allow us to solve these systems of equations. And I want to look here just for a moment and see what they choose to do. Now, I'm going to leave the book to solve for whichever variable they choose to. I'm going to solve for the variable that makes the most sense to me. There are several different ways that you can solve this problem. But the principle that we're going to do is we're going to look and we're going to say, okay, I either want to solve for x or I want to solve for y. In other words, which variable do I wish to eliminate, and what can I multiply both sides of the equation by so that I can eliminate one of those variables. So we can multiply by a negative number, we can multiply by a positive number. What I'm going to choose to do here is I'm going to say, okay, I have a y and I have a 2y. If I multiply this first equation by 2, then I can manipulate this so that these two equations will cancel out. Let me show you two different ways that I can do this. First, I can multiply this entire equation by a negative 2. How am I actually going to do that in real life if I wanted to show that with a bunch of steps? I would not have y plus x. I would have x plus y, that whole quantity times 2, is equal to 2 times 8. Then I would have 2x plus 2y is equal to 16. We've multiplied both sides of the equation by 2, so our relationship is still the same. The quantity that we have on the left side is the same as the quantity that we have on the right side. Now that we've done this, what can we do? Well, we now all of a sudden have 2x plus 2y is equal to 16, and our second equation is 3x plus 2y is equal to 22. We have the same coefficient here, we have the same sign, so if we add them together, it's not going to do us any good. We'll get to nowhere. We have 5x plus 4y is equal to 38. But if we subtract the second equation from the first equation, what are we going to have? We have 2 minus 3 gives us a negative x. 2y minus 2y is 0. 16 minus 22 gives us a what? A negative 6. That doesn't sound right, but it is. Negative x is equal to a negative 6. I divide both sides by a negative 1, and I have a value for x of 6. Okay, which is exactly what we need to do. We now have a value for x that we can substitute into one of the two original equations. We're not going to substitute it into that one that we manipulated. We're going to substitute this into one of the two original equations. Now, what happened if we, rather than multiplying both sides of this equation by a 2, we chose to multiply by a negative 2? Let's see what happens here. When we multiply both sides of this first equation by a negative 2, we have negative 2 times x plus y is equal to a negative 2 times 8. Negative 2x minus 2y is equal to negative 16. So now, let's take this equation and see what happens when we solve the system of equations simultaneously. So we have negative 2x minus 2y is equal to a negative 16. And our second equation, 3x plus 2y is 22. 3x plus 2y is 22. Whereas we subtracted over here 2 minus 2, we're going to add here so that our y variable will be eliminated because negative 2y plus 2y is 0. So I'm going to put add to remind me what I'm doing. Negative 2x plus 3x gives me x. Negative 2y plus 2y gives me 0y. The y's cancel out. Negative 16 plus 22 is a positive 6. So you see that whether we multiplied this first equation by a negative 2 or a positive 2, we still come up with the same value for x, which is 6. Now, I've written here subtract and add. I cannot emphasize enough to you the importance of putting this little extra step in here. It doesn't show up anywhere in your book. This is something that I have seen in my experience teaching and also in my experience just solving problems on my own. Write something to the left of your second equation as a mental reminder or even a physical touch point. 2 plus 3. What was I doing here? I did these backwards, didn't I? Doesn't do any good to erase my notes and then put them in wrong. So we have subtraction. Whether you use an actual subtraction sign or the words, add, or addition, put some sort of a visual cue here for you to help you say 2 minus 3 is negative 1. 2 minus 2 is 0. 16 minus 22 is negative 6. Negative 2 plus 3 is 1. Negative 2 plus 2 is 0. Negative 16 plus 22 is positive 6. It is screamingly easy. Unbelievably, oh good grief, unbelievably easy when you are working problems like this to lose track of what operation you're doing and to subtract on the left side, to add on the right side, or to lose track of these negative signs. Please take the time to write a visual cue, and it will be so worth your time. Okay, now we have a value for x over here of 6, and we can continue solving this system of equations. How do we do this? Once we have a value for one of the variables, take this value and substitute it into one of the two original equations. Which one are you going to use? Either one doesn't make any difference. Now me personally, if I see x plus y is 8, and I see 3x plus 2y is 22, why in the world would I want to use this second equation? X plus y is 8. 6 plus y is 8. Obviously y is equal to 2. So we now have a value for x, we have a value for y, and the solution to this system of equations is the ordered pair 6, 2. And what does this tell us? This gives us the location of the point of intersection of the graphs of these two lines, of these two equations, if you were to graph them on the same rectangular coordinate system. Now, how do we check to make sure that we have a true solution? You substitute this ordered pair into the original two equations. And of course, the one that you used to find the missing value of the variable had better be right. But let's look and see if this ordered pair here works as a true solution for 3x plus 2y is 22. So we have 3 times x, which is 16, plus 2 times y, which is 2. And we want to know if that is going to be equal to 22. And as you see, of course, 18 plus 4 is equal to 22. So you have verified that the ordered pair 6, 2 indicates the point on a graph at which these two lines would intersect if they were plotted on the same graph. So you validated your solution. Now let's go ahead and do the next example in our book and see what we have. This is going to be example number 2. And this is on page 297. And we have 2x plus 3y is 6. And we have 3x minus 2y is 8. 3x minus 2y is 8. And we want to be able to solve this system of equations by the addition method. Remember, subtraction is the same as adding the opposite. So when we refer to the addition method, we can either add or subtract those two equations. Now if we look at this and we think back to the example that we just did, all I had to do was multiply one of these equations by a number, and we had a variable that will cancel out. And the reason for that is we had the coefficient of one variable was a multiple of the other variable. You can just multiply 2 times 1 to get 2, but now 2 and 3 are not multiples of each other. So what are you going to have to do? You're going to have to think, okay, what is a common multiple of 2 and 3? And of course that's going to be equal to 6. So we're going to now multiply both sides of both equations by a different number. Let me show you exactly what we're going to do. I'm going to multiply this first equation here by 2. Because what I am choosing to do is eliminate the y variable. Because 2 times 3 is 6. And I'm going to go ahead and rewrite the new equation over here to the right. 2 times 2x is 4x, plus 2 times 3y is 6y, is equal to 2 times 6, which is 12. Everybody agree with that? You can see we're distributing 2 times 2x, 4x, 2 times 3y is 6y, 6 times 2 is 12. Now, if I multiply this bottom equation by 3, let's see what happens. 3 times 3x is 9x. 3 times a negative 2y is a negative 6y. 3 times 8 is 24. Now I have two equations where I see that if I add the y terms together, they're going to cancel out. Now let's go back and address for a moment how exactly is it that I can multiply one equation by 2 and one equation by 3? I thought you had to use had to do the same operation. You do. We're treating these two equations separately. First, we take our first equation. That was good. First, we take our first. What have we done here? We have multiplied the left and right hand side of that equation by 2. So we have maintained the balance of this first equation. It looks different, but it's still in balance. Then we treated our second equation individually, independently. And we multiplied the right and the left hand side of the equation by 3, giving us an equation here that looks different from our first, but it's still in balance. So you can not multiply the left-hand side of one equation by 2 and the right by 3, but you can use different multipliers on different equations. And that's an important distinction that can be a little bit challenging to grasp when you're first learning how to do these problems. Now, what am I going to do to solve these two equations? I'm going to write my little reminder here to the left that says I'm going to add 4x plus 9x is 13x, 6y minus 6y drops out, 12 plus 24 is 36, and that's not going to divide evenly, so let me make sure that I'm getting what they're asking me to get. Yes. I divide both sides of this equation by 13, and I have that x is equal to 36 over 13. That's a fairly ugly looking fraction, but 13 is prime. 13 is not a factor of 36. So this is what our value is for x. Now, how do we find our y value? Well, we're going to go back to our original equations, not to one of our multipliers. So let me go back in here and show you only our original equations. And I have 2x plus 3y is 6. 3x minus 2y is equal to 8. And I'm going to substitute x into one of these equations. Do it into whichever one you wish to. I'm going to substitute into this first equation here because I don't have to multiply that fraction by 2. So I have 2 times 36/13 plus 3y is equal to 6. I have 36 times 2 is 72. 13 plus 3y is equal to I'm going to have a common denominator, so I'm going to go ahead and rewrite 6 with a denominator of 13. So 6 times 13 is what? 78? 78 thirteenths. All right? I'm going to subtract 72 thirteenths from both sides of the equation. And I'm going to end up with 3y is equal to 6 thirteenths. 72 minus 72 cancels out. 78 thirteenths minus 72 thirteenths leaves us 6 thirteenths. Now, because I have a fraction on this side, I could still say divide both sides of the equation by 3, but when we're dealing with fractions, it's much easier to multiply by the reciprocal. So we're going to multiply both sides of this equation by 1/3. What do we have? We see that we have a y on the left-hand side of the equation. We have a common factor of 3 that reduces. And we see that y is equal to 2 thirteenths. Not a nice, convenient, even number here, is it? The point on the Cartesian coordinate system where these two lines would intersect, if you graph them together, would be where x is 36 thirteenths and y is 2 thirteenths. This is a perfect example of why you don't find the solution to systems of equations by graphing, because you're not going to be able to have that precision when you graph something with pencil and ruler on a piece of paper. So, how in the world do we know that this is true? You know where I'm going with this, don't you? You're going to check both of these equations. You're going to put your solution, substitute it in to both of your original equations. So you have 2 times 36 thirteenths plus 3 times 2 thirteenths. Is that equal to 6? Then you have to simply go through your multiplication of fractions. And you see why it's important that you're very comfortable with fractions. 2 times 36, 72 thirteenths plus 6 thirteenths. Is that equal to, remember this was our original equation, 78 thirteenths. Yes, obviously that's true. But we also have to check and make sure that this ordered pair here, 36 thirteenths, 2 thirteenths, and here goes another marker out. We have to see if 36 thirteenths and 2 thirteenths works to satisfy this second equation. So we are going to have 3 times 36 thirteenths minus 2 times 2 thirteenths. Is that equal to 8? And what is 8 thirteenths? 8 times 13, 3 eighths are 24, carry 2. It's going to be 104 thirteenths. And C, is this what we end up with? What is 3 times 36? 3 times 36, 3 sixes are 18, that's 108 thirteenths minus 4 thirteenths. 108 minus 4 is in fact 104 thirteenths. So what we have verified here is that the ordered pair 36 thirteenths, 2 thirteenths is the solution to this original system of equations. Okay? And I hope that what you saw in this example here, the example that I worked earlier, is that these problems take some time to do. but it's very straightforward. It's very methodical. You want to be careful to be very, very precise about your work. You don't want to rush through and skip steps. You want to go ahead and write yourself little visual cues that will help you to keep track of, are you adding, are you subtracting? Be, be careful to keep up with your positive and negative signs. And then if your homework instructs you, or your test instructs you to show the check, you have to do that because that's worth half the credit. If you're taking a test and it does not instruct you to check your work, be wise and check it anyway. Why would you want to hand in something on a test and have it be wrong when if you had taken a little bit of extra time to do your check? You'd know for yourself that when you handed in your test that you had your answers correct. Okay, so that's the last example I'm going to work. I'm going to review some vocabulary for you, which we've been talking about. I used it in class a little bit. It was on the videos. And you will be required on your tests to be able to understand consistent, inconsistent, dependent, independent, and the algebraic relationship between these. So let me go ahead and look on page 298 and see how I want to describe this for you. As I've been reminding you and covering in these videos, lines can interact with one another in one of three ways. The first way the two lines can interact with one another is that they can be parallel. Okay? And there are how many solutions here? How many places do these two lines intersect? How many places in space do these two lines occupy the same space? There are none. So there is no solution available. And if there is no solution available to if there's no place where these two lines are going to occupy the same space, we call that an inconsistent system of equation. Inconsistent means that there is no solution. And you're going to be required to be able to identify inconsistent systems of equations. And when you solve, this showed up in section 7.4, but when you end up trying to add your equations, your two equations together, you're going to end up with a false statement. You're going to end up with something like 0 is equal to 5, negative 2 is equal to 17/3. Parallel lines have no solution because they do not intersect anywhere in space. We describe the relationship as being inconsistent because there is no solution. The result that you get when you try to add those two equations together is a false arithmetic statement. 0 is equal to 5. Here's an example that I'm going to write for you very quickly. 2x minus 2y is equal to 4x minus y. Okay, 2x plus 2y is 4x plus y is 2, and this is what I get for coming up with an equation with an example off my head. These are lines that are collinear. Those are not lines that are parallel. Would be y is equal to x plus 1, y is equal to x plus 2. Okay, I'm thinking ahead. Now let me go ahead and write this in the form where I have negative x plus y is 1, negative x plus y is 2. And what these two lines actually are is these are lines with a y-intercept of 1 and a slope of positive 1, y-intercept of 2 and a slope of positive 2, so you should be able to see that those are going to be parallel lines. But let's just add these equations together, and let's just go ahead and subtract them. What do I end up with? Negative x minus a negative x. and I'm going to end up with no x, 0x, y minus y plus 0y is equal to 3. That's a false statement. We have 0 is equal to 3. False statement indicates that these lines are parallel. Another way that lines can interact with one another is they can intersect at one point in space. This is by far the most common way that lines are going to relate to each other. There's one and only one solution. We describe the relationship between systems of equations that have a solution. If they have a solution, we say that they are consistent. Consistent means there is a solution. We have two different types of consistent solutions. We have independent solutions and we have dependent solutions. And independent solutions have you can think makes sense independent. If you're independent, one is working alone. If you're dependent on others, you have a group. Consistent independent systems of equations have one solution only, and this is where you're going to have your answer is going to be, let me see how they describe it. You know, a statement that contains a variable and a value. An example here might be something like x is equal to 6 or y is equal to 1/3. What we have here is what results when you add those two equations together. Lines that intersect in one place obviously have one solution. They're considered to be consistent, which means that they have at least one solution. When we say that the system is independent, you know that they have a solution and they have only one solution. Therefore, the lines have to be intersecting lines, and I'm getting ready to sneeze. Oh, what I wouldn't give to have a remote to this video. I apologize for that. And the last way that lines can interact with one another is they can be collinear. They can occupy the same place in space. One line right on top of the other. And there are an infinite number of solutions, not simply many solutions, but an infinite number of solutions. Because there is at least one solution, we say that those systems of equations are consistent. Because there are many solutions, in fact an infinite number of solutions, we say that they are dependent. And when we add those two equations together, you end up with a true mathematical statement, something like 6 is equal to 6. And let me go ahead and show you an example now of two lines that are parallel. 2x plus 2y is equal to 4. X plus y is equal to x plus y is equal to 2. And let's say that we wanted to subtract. We're going to have to multiply this second equation by 2, aren't we? And when we multiply this second equation by 2, what do we end up with? Let's see if I can make this actually work in my head. This is another one of, we end up with a true statement, 0 is equal to 0. Let's see. X plus y is equal to 2. When we multiply that by 2, look at what we get. We end up with exactly the same equation. When you subtract that, 2x minus 2x is 0. 2y minus 2y is 0. So you have 0 is equal to 4 minus 4, which is 0. So you end up with this true algebraic statement here that 0 is equal to 0. So this chart right here that I've put together. This describes for you the relationships between a system of parallel lines, a system of intersecting lines, and a system of lines where they are collinear. These are collinear, and I'm not sure that's spelled right. It may have only one L. We have lines here that are intersecting, and we have lines here that are parallel. You will need to put the time into learning what it means if we say a line is inconsistent, a system is inconsistent, if we say a system of equations has infinite solutions, or if we end up, when we add those two equations together and we end up with a true mathematical statement, what does that tell us? So that's the end of section 7.6, and I will see you on Friday.